Morning.
Hello.
No.
Am I the only person here?
No. There's
Oh.
7 participants, including me. 6 students. I'm going to make this a little bigger. Got a nice lesson today. We'll have challenges. Okay, I think you can kind of see that. I guess I can make this bigger just for this one problem.
I can't see it. Like,
Orange. Now can you?
no. I mean, like, barely, but, like,
I
it's
just
very
made it 250. Want to make it 300?
Yeah, I can't really see it well.
That's 300.
Yeah, I guess that works. Yeah, it works. Is that p plus 3 squared?
Uh-huh. Quantity.
Okay. Oh, we're foiling, I guess.
A spider's silk is stronger than steel.
Stronger than what?
Stronger than steel.
Oh, really?
How do
Is
they
it?
measure that strongness?
The strength, I don't know. Maybe they're wrong.
Yeah.
Maybe they're right.
Hi.
Hi.
Joe, move your mic. Joe, move your mic.
Please take a second. Maybe you guys can tell me, does me turning off that light make things worse?
Not really. Doesn't make it better either.
Anybody else? Let me turn it back on. Light better? No difference? Worse?
I mean, I would prefer the light on without light off because if you turn it off, then there's like a shadow on the board.
I see. When the light's off, there's a shadow.
Yes.
Let me see. Oh, yeah. This, yeah, totally. That gets rid of the shadow. You're right. Yep. On it is. Yeah, I mean, as a studio, this is not a great space. I do have the advantage of a TV above. If I can't do it in my living room because my kids are out there playing. Not in my office because my wife works in there. So kind of this is what I'm limited to. Hopefully you guys have the lesson out printed or you can see it so you're not relying on my screen. You just kind of see what's on there so you can turn to the same page, I guess is the idea. Hope that makes sense. I have something for you guys to look at. Everybody draw a unit circle.
Yeah, trig. And radians.
Oh, look at that. I missed. It's almost like my mind purposely went around that point.
Like, nee, oink, nee.
Yeah, that's called psyching yourself out. Just have faith and go straight and don't overthink it, trying to aim. They ruined it. Better? Oh, went like down. It's not a smart board, so it's actual marker on the board.
It's not a smart board, it's a dumb board.
It's a dumb board. Dumb board. That will have to do. Okay,
Mr. Rosenthal.
that's me.
The retakes are tomorrow, correct?
The retakes are tomorrow, correct.
At 2 or 3?
They're going to be from 3 to 4:30.
Okay, thank you.
Look in the updates. I also put it in there. Try to draw that. What is this vertical one labeled?
What?
What do I label this vertical one here?
Square root of 2.
No.
Well, we need to find an
Sine
angle
theta.
first. We need to determine the
This,
angle.
this height is not the same as this. This is not an isosceles.
The radius is equal to 1 and throughout
That's-
the
I
whole
already-
entire unit
I
circle.
already have the radius one here.
Wait, I think I have the
Opposite.
unit circle in my other folders.
Don't look at it. Try to think about it.
The
Don't.
vertical one would be and the horizontal one would be cosine theta, right?
That's correct. If you have trouble with that, label it y for vertical and x, and then see if you can solve for y. So if this one's y, sine of theta is equal to y over 1. So y is equal to sine. Cosine of theta would be x over 1. So x is equal to cosine of theta.
Y over x is tangent.
Well, we're going to talk about that. Now I want you to do something new. I want you to extend this radius out beyond the circle. Okay. And then from this point, I want you to go perpendicular until it meets there. Now, I want to know what this is. I want to know what that is, and I want to know what that is. See if you can work on that. What are those? How can you label those? See if you guys can figure that out. I like that warm up better. We can call it, find out what this H is. We get this off of there. Let's find out what this, so H for hypotenuse of the purple one. Find out what this O is and find out what this adjacent is. Once you get one, tell me.
O is equal to tangent of theta.
How did you get that? You are correct.
I got it. I did tangent of theta is equal to O over 1.
Because A is equal to 1 because it's now the radius.
X
Why?
or A.
Wait. Let Zig do this. Tangent of theta is what?
Tangent of theta is equal to O over 1
Why?
because it's tangent and so it's opposite over adjacent. And the adjacent of tangent of
Oh, you're
theta
calling this.
is
Oh, okay.
yes.
So you're saying that this is 1
Yes.
because it's a radius. That's a very simple answer, isn't it? Yeah,
Yes.
that's a great answer. I had a different way to do it. Tangent of theta is O over A. We know A is 1, right? It's a radius, right? If you look at it, A is just from the center to the edge. It's A is 1. Okay, so then you did
Sine is tangent over H.
O over 1, which is just O. So O is equal to tangent theta. Now I'm going to show you a different way that I got that. I shouldn't have started this problem early. I should have waited.
Also got H.
I feel like
H is equal to tan theta over sine theta.
Okay.
Because sine is equal to O over H. And since we found out that O is equal to tangent of theta, then we put it into the problem and say sine of theta is equal to tangent of theta over H. And then
solve
you,
for H.
what?
And you swap them. Yeah.
Yeah.
Mm-hmm. I had a different way to go about this. I had a similar triangle way of doing it. I said that to get this cosine segment to stretch to 1, you would multiply it by a scale factor. And that would get you to 1. This would grow out to there by multiplying it by some scale factor, because this other triangle in purple is a dilation of the pink one.
Yeah.
All right. So then I can do this same scale. If I can find the scale factor, I can multiply every side of my pink triangle by the same K. But because cosine grows out to the edge of the circle, it becomes 1. And now solve for K. Divide by cosine. Okay. And this we define as the secant. So you get a new term out of that by doing it this way. Okay, so multiplying by secant theta will enlarge each side of the pink to get to the new bigger triangle. All right?
And if sine times 1 over cosine equals sine of a cosine, which equals tangent.
You got it. You're already there. Okay, so let's expand our vertical side sine to get to from this segment to the bigger purple one. You'll have to take sine theta and multiply it by the same scale factor. Okay, so sine theta times secant theta, which is, we said secant theta is 1 over cosine. So sine theta times 1 over cosine theta is sine theta over cosine theta, which we said earlier in an earlier lesson is tangent. Okay, so that means that O becomes tangent theta. This is 1. All right, let's do the same thing for our hypotenuse of pink. That's going to be multiplied 1 times the scale factor of secant is just secant. So this segment here is secant theta. Okay, and now the lesson has begun. Now, today we're going to learn, we are applying what we learned about right triangles thus far, and we're going to now apply it to circles.
By the way, I have my sphere warm up thing.
This one up here?
No, the sphere.
Oh, the sphere warm up. Okay, let's hold for that. We have a lot to do in this lesson today. Let's hold that. Keep it and keep asking me. Okay, thank you for reminding me. Asking me, I will get to it. Okay, so there's two new parts that I want to focus on for this chapter going into 12.1 today. We're now going to expand our understanding of tangent. As you see, if you push this and dilate this out so that you have a segment here that intersects the circle at one point, you get what we just proved to be tangent. So now tangent of an angle here is going to now mean something for segments intersecting circles at one point. And that's going to be how we define what tangent of a circle is. Tangent of a circle is going to be any segment or line or ray that intersects the circle at one point. It's going to be this purple segment here, which we now know is, we can get that to be the tangent of the angle. Okay, so, and then secant, which you're not going to be doing too much until you get to trigonometry, is that 1 over cosine is secant. But we're going to define a secant as a line that intersects a circle, and it's going to hit that circle in 2 points, which is going to be this line. If you go all the way through, it's going to make contact with the circle in 2 locations. Okay, so the secant line is going to do that. The tangent line is going to be this one that just touches the circle at 1 point only. Okay, and it's perpendicular. These are some concepts we're going to go through this section, and the secant we'll use later in some other sections. But chapter 12 is going to be moving into circles and lines that intersect within them and outside of them. You know, this will be helpful with gears and engineering and other sciences. So this will be the last chapter also. All right, so we're heading into the last.
Algebra 2.
Yeah, we're heading into the last chapter of geometry here with
Wait,
lots.
so then this class shouldn't be called geometry anymore.
Yeah, I know, right? But it is the course is still geometry. So
Wait, so if we finish this chapter by probably, like, if we're going by the fact that we're doing one lesson every day, then chances are we'll probably finish geometry by next week.
well, I'm hoping to slow down and answer more questions, and people that are confused, I want them to ask questions. Okay. Any questions about this particular thing? This is a little bit more difficult than what you see on the screen up above. That's the review of some algebraic concepts you'll need to take with you into this chapter.
Yeah, you know how I got that h is equal to tangent of theta over sine of theta? Is that the same as a secant?
Secant is 1 over
1
cosine.
over cosine.
Yeah, but what I got looks like it'd be correct, but I got tangent of theta over sine of theta.
Yeah.
Would that
Okay,
also
so
be a
what,
secant?
but okay, so look down here. What does this say? What is tangent of theta? Okay, so what did you say you got? You said sine of theta here is equal to O opposite over H, O over H. And I'm going to angle this down now. Okay, now that we know that O is tangent theta, let's replace that. H was, what did you say H was? Oh, you just said H, and then you solve for H, right? So when you solve for H, these two swap out, right? So you get H is equal to tangent of theta over sine of theta. Now, what is tangent of theta? That's sine of theta over cosine of theta divided by sine of theta. Or I could say multiplied by 1 over sine of theta, right? That's the same as divided by sine of theta. This divided by sine of theta is the same as multiplying by 1 over sine of theta. So what happens, Zig? And you get 1 over cosine, which is secant. Right? You see it? Zig? You see it?
Yeah.
Okay. All right, let's move on to this. If you didn't do this already.
Drosta.
What was that, David?
Oh no, that was me.
Oh,
I was just going to ask. So how did you derive how did you derive it to be equivalent to the tangent theta over sine theta?
here.
I mean, yes.
Did you see this sine of theta, what it's equal to for the big triangle?
Oh right, yeah. Never
O
mind.
over h, right? O was
Mhm.
tangent theta, h we didn't know. And then these swap out with the properties of proportions.
Yeah, thank you, Mr. Drosta.
Anybody else? There's a meeting number and password. Every Zoom meeting you participate in, bookmarks it in your menu. Okay, there's some other chat going on. Okay. I do prefer, I don't always remember to look down. I prefer, if you can, to just communicate with me by just asking a question live. But if you're really uncomfortable, that's fine. I may not look at the chat though. Anyway, it varies. All right.
Someone else asked if you could repost the Zoom information, and so they were just talking about how they could
Why
bookmark
should they
it.
do that? If I hear a good rationale for doing that, I would do it. But I have not heard a good rationale for doing that yet. People don't want to scroll down. It's not a two-way communication where we have this long chat thread. It's a small thread of only a one-way communication of updates from me to you guys. Not only that, once you go down and get it one time, you should copy and paste it somewhere where it's readily available, either in your phone or in a Word document or anything, really. There are myriad choices with that regard. So I just don't see a good rationale for me needing to keep reposting stuff for you guys. Okay? All right. P plus 3. Let's just go through this quickly. Squared. What does it mean? It means P plus 3 times P plus 3. Of course, we have Pascal's triangle. Hold on, let me close my window. Hey, George. All right, so P plus 3 times P plus 3 is what P plus 3 squared is. I just wanted to make sure when we move forward that you guys aren't doing the number one error, which is that if you don't see it this way, if you just skip that part, students want to skip this part, they just want to do this, P squared plus 9, which is incorrect, of course. We want to avoid that. Of course, it's a binomial. Squared means a binomial times a binomial. What you get out of it is 4 products. Product 1, product 2, product 3, and product 4. And then the 2 middle products combine. Okay, to get that. Now I don't want to do this every time. That's too long. We need to be doing this much quicker, much more quickly. Right, Søren?
Yes, Mr. Drosta, you caught yourself quickly with that one.
Ah, very good.
Wait, wasn't that foil?
Respond. The what?
Wasn't that
Yes.
foil?
Yes, that was.
Mr. Knauss's favorite.
We don't need to call it any name. No name calling. Okay. So with any A plus B, even if it's complicated, even if A is made up of a bunch of stuff and negatives and ton of variables, doesn't matter how complex A actually ends up being. When you square this, it's A squared plus 2 middle terms that combine. So you're going to get 2 identical middle terms that will combine to make 2 middle terms. Okay, plus that. So if you use that every time, this is what students forget. They forget that part. Okay, now that we know this, by the way, in Pascal's triangle, this is the 1, the 2, and the 1. So you have 1, 1, 1, 2. That's it right there. This is a plus b to the 0 power is equal to 1. A plus b to the first power is equal to 1a plus 1b. A plus b squared is equal to 1a squared plus 2ab plus 1b squared. Okay, next layer of Pascal's triangle. 1 plus 2 is 3, 2 plus 1 is 3, and a 1 always on the edge. Okay, those are your coefficients. This is a plus b cubed. If you wanted to cube it, that's a plus b times a plus b times a plus b. Then what would this be? 1a squared plus 3a.
It'd be 1a cubed.
Yep, cubed, thank you. 1a cubed plus 3a squared b.
And 3ab squared
Hey, by the
and
way,
1b cubed.
Look at this. I could do this. Look at this. 1a cubed b to the 0.
It's just 1.
Yeah, which is just 1. Then this one comes down and this one goes up. And then this goes down and this one goes up. And then a goes to 0 and b goes to 3. Of course, we don't need that and we don't need that. All right? And then you can just keep doing your Pascal's triangle to get more of them. But that's not what we're working on. We're just keeping it simple.
Kind of like that, I figured out a way, like just like the squares, you add the first number, then you add the second. For cubes, you add stuff. I forget right now, but
You add stuff. I like that. Okay, so this one is w squared. So what I do is I multiply these. I get 10w, and then I double it. So 20w plus 100. Questions? And done. And then last one, when there's a minus, take a look at that. M squared. Negative 2 times m is negative 2m. Doubled is negative 4m. Negative 2 squared is positive 4. Okay, you got to know that. You got to know it well. Looks like we're getting fewer and fewer participants. I don't know what's going on. People need to show up. We're missing.
now we only have 40 people.
We need 60 more students. that are
People
not-
like to sleep in.
I think people like watching it later in the day or something. Maybe
Well,
they
they
don't wanna
must
wake
be.
up.
They must be thinking that they
Like-
don't. They must be
It's-
thinking that they don't need to ask live questions.
It's hard to wake up in the morning.
Now, I
No, it isn't.
would say, as my
I
own,
wake up at
It's
7 o'clock
not.
every
You're
day.
supposed to
for
wake
all
up.
of you,
at
wait a minute,
7.
they're going to see this
Hold on.
video. For all of you watching it later, I really, really prefer you watch it live. Try it. Watching it live, I really, really want you to get up in the morning and get dressed and do all your stuff that you need to do. And
I'm
get
not
here-
dressed. I
Get
have
here,
a
okay,
pajama.
but you should. And get here live for the video. Treat it like school, because it is. Okay, so all of you watching this video who are going to see this later, Mr. Rosenthal really wants you to log in. Okay, every time, every day, not just some days, every day. I would love to see participants jump into the 60s, which we have not done yet. Okay, I would love to see it go further. So please, if you're seeing this later, get in here live if you can. Different experience. Okay, here we go, moving along. Okay, we also want to make sure you can do this. Right triangles, I almost don't even want to stop and do this. Right triangle with legs of 16 units and 8 units. I'm going to have to shrink this down. 200.
Yes, and the camera isn't facing the problem, Mr.
Okay,
Rosenthal.
yeah, well, it won't matter because it was too large anyway. It was off the screen. Okay, so forget the orange instructions. You're just finding the missing side of a right triangle. So what would the missing side be? I want to see if you guys have your skills for simplifying radical expressions. I want to make sure you have that too. So let's just do that, kind of warm up. David, you can't say that on the chat, okay? Thank you.
Okay.
He kind of had a good reason though.
Yeah, well, in the first place, we don't need to be saying things that don't pertain to the lesson. you're finding the missing side of the right triangle. And really it's not that we're testing you on a Pythagorean theorem, which you need to know, but do you know how to successfully simplify radical expressions? And for the most part, the answer to that is yes, but there are some students that are still rusty with that type of activity. That's the first one. $320. So look for perfect square factors. Okay. There we go. So the square root of that, square root of that, square root of that. Square root of that's 4, square root of that's 2, and I'm not going to take the square root of 5. That's kind of how I go about doing these problems. Are there any questions about the first one? 8 rad 5 would be the hypotenuse. Anybody? Oh yeah, somebody got it there, 8 root 5. Okay, no questions. I'm going to move on to the second one. Let's see, a leg of 13 units and a hypotenuse of 17 units. So notice I'm going to take the hypotenuse squared and subtract the leg squared and take the square root. The hypotenuse squared minus the square of a leg gives you the other square of the leg. Then I square root it. What's 17 squared? Is it 289 or something like that? Something silly like that?
289.
Yes, it's 289. 13 squared is 160.
Okay, so that's 120. Okay, so I'm looking for perfect square factors, so I can pull a 4 out. And
That's it.
that's it, yeah, because you'll get 2 and 15 and 3 and 5, and you don't have, these are all prime factors, and you don't have any repeats.
Factor 4 into 2 times 2, though. If you factor 4 into 2 times 2.
It's going to be like that. I'm going to take the square root of those and forget
2
all.
rad 30.
Okay, so this will be 2 rad 30. Questions about that?
Well, Mr. Rosedale, you could have also gotten the answer by 120 into 6 times 20, or that if that produces 2 2's, then you could do 2 times square root of 30, and 30 would be the product of. Oh yeah, so it would be the product of what you ignored.
Yeah, I mean, there are many ways to break down 120. 120 has many factors. 5 times 24, right? You'd get that 5 out, and you'd be left with all these other factors, okay? But there are so many ways to break down the 120. So what I do is I'm searching for perfect squares is what I'm doing, and that makes it a little bit faster.
The next one you can simplify by a factor of 4.
Well, we're not on the next one yet. We're about to.
What?
You're very close, but we're not there yet. Okay, leg of 16, hypotenuse of 20. Again, I'm going to square the hypotenuse and subtract the square of the leg. Okay. So another thing you could do, watch this. This is 20 times 20 minus 16 times 16, right?
It's a perfect square, I think.
You could factor.
It is.
What do you mean it's, oh, you mean the solution is?
Mhm.
There's a 5 in here that's not in there. Oh, but when you subtract them, okay, I see.
Yeah.
But what I could have said is that there's a 4 that goes into both of these.
Yeah,
Well,
that's what I said. Simplify them by a
I
factor
factored out a 4 right now. Now, how does that work if I factor out a 4? I don't get to factor it out of both of these, do I?
Yes, you do.
I do, don't I? Okay. So I think that makes it more complicated than it needs to be. So I don't want to go that way. Okay,
Simplify it first so you get a Pythagorean triple.
400 minus, oh, you're right. Look at that. Take a 4 out, you get a 4. Take a 4 out, you get a 5. So then, yeah, it'll be 12, right? The other side. Okay, great. So here is 256. So when you subtract, you get 144, which is 12. Okay? Good work.
Sphere problem.
All right. Anybody questions with this? What
Sphere
is the
problem.
chapter of this about? Circles. I think you might have missed the opening, Mark. But we're going to be talking about circles and the lines that intersect them and the
Sphere
application.
problem.
And then we're going to talk about the applications of that in engineering. Okay.
Sphere problem.
Okay, I need to shrink this down a lot. Let's go to 175. And that might not even be enough. It might. Let's see. Yeah, I think we're good. Okay, here we go. In chapter 8, you studied the tangent ratio in right triangles. The tangents you will study here relate to circles. And we just made that connection in our warm-up today. Okay, if you didn't see it, go back to the video later and you'll see how we set the whole thing up from the beginning to the end. Okay, and you can always ask me during office hours, which are right after the lesson, but really it's all day long. If you send me messages, I keep checking my computer frequently throughout the day. I should be able to answer any questions that you have throughout the day. All right, a tangent to a circle is a line in the plane of the circle that so you can't have a circle in the plane of this board, okay, and then I'm coming from outside the board, cutting through the circle that way and touching it. That's not what they're talking about with the tangent. It's a line in the same plane that the circle is in, that intersects the circle in exactly one point. And we saw with using our trigonometry that we ended up labeling that and proving that that was a tangent of the angle form. Okay, but here a little bit different. It's going to be that it's a line with, right, that has no length to it. It's infinite in both directions. It's a line that intersects the circle in the plane at exactly one point. Okay, so here's a circle, pick a point, there's going to be a line, and there's really only going to be one line. There's exactly one line tangent at that point. There's not some other line that is also tangent at the same point. Okay, so only one at a time at one point in one location. Okay. What you don't see here, later on, we'll have it in the actual vocabulary, which we're not going to have vocabulary on your test. I'll probably have to say that over and over. But there's another type of line. Well, you could have a line that doesn't intersect at all, right? But then you have a line that any other line that intersects the circle that is not a tangent has to be a secant. And there's going to be 2 points of contact with the circle. If it makes more than two contacts, that means it's not a line. It would have to curve back around. So at most, a line can only contact the circle in 2 locations. Okay, so it's either 1 or 2 or nothing, right? Those are your 3 examples of how lines are going to interact with circles in the chapter we're studying.
When it touches 1 and when it touches 2, what is it called?
Ah, good. Okay, so this one is called a secant.
So it's defined by 2 intersection points?
That's an interesting question. Is the secant defined by 2? Well, through any 2 points, there's exactly one line. So I guess you would say that those 2 points could define that line, but some other 2 points that are on that line could define the line as well. So it defines the line that we're talking about in the context of the problem we're talking about, which is the circle. So it's really, we're talking about the relationship between these lines and the circle that they interact with.
That line right there that hits the circle at 2 points, that's 1 over cosine?
Yeah. That's that one that we made that with the unit circle that extended. Here's the radius that we had, and it went out past the circle. Remember, that was the hypotenuse of the big purple one, right? And what was that one doing? It was cutting through the circle. So the one that cuts through the circle, tangent doesn't cut through the circle. Any line that cuts through the circle is the secant line. Okay? All right.
Like a diameter.
Just some, well, it could be a diameter, right? A diameter sits on some secant line. The secant line, there are secant lines that contain diameters. Okay.
An infinite number of
Say that again.
Infinite number of secants that are diameter.
Yes, because there are infinite diameters. Okay, are you guys ready for your first theorem? Back to proofs, folks.
Oh.
Back to proofs. Yeah.
Actually, that ain't that bad, actually. Never mind.
Yes, they
All
are.
right.
Well, Mr. Rosenthal said, like, there are not going to be any more hard proofs anymore. So that's
I
great,
don't know if I said
Yes, there are.
I'm pretty,
I think
pretty
there
sure
are.
you said that.
There are.
They're nothing like as extensive as HL. Okay, let's look here at this picture. You have this ray, BA is a tangent ray, you can call it. We're still doing terminology here. You could say this segment here, BA, is a tangent segment. And of course, line BA is a tangent line. What is B by itself called? The point of
Tangency.
that is the point of tangency. Okay, so B is the point of tangency. All right, just some terminology you're going to hear. We're going to be talking about these things a lot. So, okay, 12.1. If a line is tangent to a circle, then the line has to be perpendicular to the radius drawn to the point of tangency. So, if AB, this line, is tangent to the circle O, then when you draw O to point P, which is the point of tangency, it must be perpendicular. That's what it's saying. All right, that's what 12.1 is saying. So let's read it again, just so you can get it in your head. If a line is tangent to a circle, because we're going to do a converse, 12.2 is going to be the converse of this. So 12.1, if we start knowing the line is tangent, then it is perpendicular to the radius drawn to the point of tangency. In this case, point P. So we would say line AB, which is the tangent line, is perpendicular to the radius OP. P being a point, the point of tangency, it has to lie on the line AB. Okay? All right, how on earth are we going to prove that? Any ideas?
Sphere problem.
Not a sphere. We've gone away from three-dimensional now.
Using a triangle.
We are done for the year with 3 dimensions.
I know, but
Can you construct a line perpendicular to the radius?
Say that again, Daniel?
Can you construct a line perpendicular to the radius?
You already have one. Oh, you mean before you know that. Okay.
To prove it, yeah.
How do you know it's going to go through the center? Or if you construct it perpendicular through that point, how do you know it's going to go also through point P? So once you choose P, how do you know it's going to go through O? And once you choose O, so we have 2 constructions. We have a construction where we construct a line perpendicular to the red line through a point off the line, through O. But you can't, in that construction, you don't know it's going to go through 2 points. You know it's going to go through O only. Or the other construction is to construct a line perpendicular to the red line through a point on the line, P, but then you don't know if it's going to go through O. You don't get them both. You can pick one, but not both at the same time.
what if we draw the radius through O and hitting P, and
All right.
then we draw
Hold
the
on.
tangent?
Let's try that. So here's P, here's A, here's B. You have.
We're drawing the radius first.
Okay, what do you want me to do? Draw a radius to point P. Fine. You don't know if it's perpendicular or not.
No, I'm saying do the radius first.
Yeah.
Then construct a line perpendicular to that through point P.
At that point, okay, then how do you know that that's a tangent line? Oh, but wait a minute. Then you're doing the converse, aren't you? You have to first start with a tangent line. Then what you're trying to do, you're saying, okay, I constructed this perpendicular, then you're trying to prove that it's tangent. That's different. You're starting with that's tangent. So you can't do it that way. I have the proof on the next page. Any ideas?
How about you assume it's not perpendicular?
Ah, I love it. You guys are using indirect reasoning that when you're doing that. Okay, you're trying to prove that it is, assume that it's not, and show that that can't be the case. That would be interesting.
What if when we construct the line, it just turns out to be perpendicular?
Construct
Daniel,
the
if
line
you're
and
an
measure the
intellect,
angle.
How about we use how about we construct the line between from O to A and use Pythagorean theorem to prove if
That's what I was.
Wait,
That's what I was thinking.
you don't know. You mean the converse of the Pythagorean theorem?
yeah, the converse of the Pythagorean theorem.
Okay, what would I label
You don't know the side lengths.
You don't know the side lengths.
You do if you have that angle. You could say, oh, that angle is you know each of the side lengths in terms of trigonometry. So you could say, oh, AP is the tangent of theta, and AO is secant of theta.
You don't know if it's tangent theta unless this is a unit circle. It would be times k times some scale factor, right? And that scale factor would be determined by what, right? By how much larger, by how many times larger or smaller this radius actually is than the unit, than 1. Okay, so I guess, so it would be r tangent theta is what it would be, right? Okay, so instead of trying to do that, let's go on and let's try to look at it on the next page. You guys ready? Okay. So now my challenge here is that it's going on the page, and it's hard to see already.
right?
So I don't want to make it any smaller than it already is. Okay?
It doesn't really matter because you should be in your own room.
Okay, so here, listen to this. Line N is tangent to circle O at point P. Here's line N. It's going to be tangent to circle O at this point P. Okay? Okay, so that's it. Assume that line N is not, so whoever said that, the indirect reasoning is the way we're going to do it.
Okay.
Assume that line N is not perpendicular to OP. All right? All right, if line N is not perpendicular to OP, some other segment, OL, there has to be some segment that exists that is perpendicular to line N through point O. And if it's not this one, then it's got to be some other one. Okay? So there you have that. So let me recreate this on the board. This is where we can take our time. We're not in a rush. So here's circle O. Here's line N. Tangent at P. And assume that OP is not perpendicular to line N. Then there exists some other line, they're saying, that's not going to look very nice, that is perpendicular. Okay? And we'll say that that's perpendicular at some other point called L. Because we know by construction that we can construct a line perpendicular to N through a point O off the line. All right? So we know by construction that that's there. There exists some perpendicular segment that connects them. And if we're assuming that it's not this one, then it's got to be some other one, and we're going to call that one OL. Got it? By the ruler postulate, there is some point K out there that on PL, which is on line N, such that the distance from P to K is equal to 2 times the distance from P to L. How would we do that? Take your compass, right? Measure from P to L, right? And then bring it over here and measure.
They take that distance from L to K.
Yeah, so the L to K, basically you can do this by construction. You don't have to say ruler postulate. You can construct LK along this line congruent to PL. PL and LK are congruent by construction. Okay, hopefully you're following. Okay, let's read on. So PL is equal to what? PL is equal to what?
LK.
LK. So that's by the definition of congruency. Okay, now let's look at triangles. Triangle OPL. So let's actually draw this out and make this triangle here. Triangle OPL is congruent to triangle OKL. Why? If this is perpendicular,
SAS.
you have this segment is congruent to itself, right? All right angles are congruent here.
Wait,
right?
is this SAS?
These two triangles, yeah, it is. So you have this side, this angle, and these sides. So by SAS, those triangles are congruent. And you're about to see something happen here. Maybe some of you already see it. So OP has to be congruent to OK by what?
CPCTC. I don't know.
CTC.
I
So
don't know.
OP and OK are equal. All right? By the definition of congruency. Since P and K are both equidistant from O, both K and P must therefore be on the circle, since we started with point P is on the circle, right? Point P was started off being...
That contradicts.
That was the point of tangency, which means by definition it's on the circle. So if K is the same distance from O, right, and that's how we define a circle, it's the set of all the points that are equidistant, right? So that means K, if it's equidistant, that's one, it's all the points, right? The circle is all of those points. So K is also on the circle, which would mean that you are contradicting the first thing that we said. It contradicts the given. What was the given?
That wasn't perpendicular.
Line N is tangent to...
Yeah, this was given as a
equal
tangent line.
P.
And by the definition, that's why we started with the definition. The definition of a tangent line is that it intersects the circle at one point. But here, P and K are both on the circle, theoretically. And so this becomes a secant line, which is a contradiction. Therefore, our first assumption must be false. What was our first assumption?
That it wasn't perpendicular?
No, that OP was not perpendicular was our first assumption, which led us further down the line to a contradiction that can't be true. Therefore, since that assumption is false, then the only thing that could be true is that OP is perpendicular. Okay? And that's the proof. Not on your test.
Oh, thank God.
That's fine.
Right? Now, if it was on your test, let's say that it is on your test. It might look like this, where it's a fill in the blank. Okay, you could probably handle it with a fill in the blank. It would be nice if you could do the proof on your own. I think a lot of you can. You just don't realize you can. Okay.
Sphere problem.
Any questions?
Sphere problem.
What problem?
Sphere problem.
Why?
Because.
David, if you
Not
keep
right
asking,
now.
he's not going to want to do it.
Yeah, I want to
Keep asking.
I want some momentum. I want to keep going. Okay.
They keep asking at a later date.
Yeah, you can use Theorem 12.1 to solve problems involving tangents to circles. So let's see how we apply this. Aha, okay, figure this problem out. Take about a minute. You probably won't need a minute. Go. I'm gonna clean my eraser.
Hello.
Wow.
How you doing?
Wow, there was a lot of gunk in the eraser.
Thank you.
Oh yeah, there we go, nice and smooth. Okay, that's 59, 60. Okay, that's a minute. So let's see what we got here. What did we learn that will allow us to find out the measure of angle x? Or measure of angle x?
Tangents are tangent lines are perpendicular to the radius from they're perpendicular.
Okay, so you got that's 90, that's 90, that's 117. So now, how do you get x?
Subtract 360 minus 117 plus plus 90 plus 90.
Okay, but if you already know that these are 90 and 90, and that the whole quadrilateral has
Oh, 117. No, 180 minus 117.
Okay, so what you're saying is that these have to be supplementary. So
Yes.
whenever two tangents come from a point outside the circle, forming this object here, these two must be supplementary because these both are going to be 90 and 90. 90 and 90 is 180, which takes up 180 out of the 360. So 360 for the entire quadrilateral minus those two angles leaves you will always leave you with 180. So these two always have to add up to 180. They're always supplementary. So really a problem like this is just quickly find, and this one is a test problem. You will see this problem on a test. Okay? So all you have to do is, that's a supplement to that. All right, and the supplement to that is 63. All right, any questions about that? No? Okay. Try this one.
I thought that.
Nope.
Too slow.
It was on the slow side. Okay, can you guys see that?
Game.
Oh yeah, we don't play that anymore.
I lost the game.
I lost the game.
Nobody plays the game.
I lost the game.
Everybody plays the game. Snapple fact, Mr. Rosenthal.
Yeah, spider webs are stronger than steel.
I knew that already.
We already knew that.
Well, you asked me.
Well, I mean, they're stronger than steel, like, comparatively, but if it was steel versus, like, a spider web, steel would be, like, stronger because there's more of it.
Okay, so now you have this angle here is 38. But that's fine because you know what this angle is. All right, and so these two would be complementary. All right, so then these two have to add up to 90, which would make this 52 degrees. Any questions about that? So these are not trying problems. These are, as long as you what it really depends on is you knowing that that's a right angle. That's it. Once you know that's a right angle, you're good. It looks like a right angle. So even if you didn't show up here today, or ever see this, you could probably do this problem by just guessing that that's going to be a right angle. All right? But you're not guessing because you know it is. Yeah.
How does the theorem that we did tell us that that's a 90-degree triangle if it says that is perpendicular from the radius from the point of radius to the never mind.
You're assuming, what are we
Daniel,
assuming that's a tangent segment. Then it must be perpendicular to this radius, drawn to this point of tangency. Okay, moving along. Yeah, we're not going to finish this lesson today, which is fine. I'm totally fine with that. Here, okay, let's do an engineering problem. This one is challenging. I like this problem a ton. Hopefully I can make it.
Oh wait, now that I think of the bicycle chains, like they
Yes,
do.
okay. So you think of these gears, right, on a bicycle attached and going around, okay? What is the distance between the centers? Okay, see if you can find that. Now, are the numbers readable, legible? Let me make it a little bit bigger.
Okay, you make it bigger. I can't see.
How about now? I can
Yeah.
redraw. Let me redraw.
26.5, 2.4, 9.3.
Good. Okay, 2.4 inches. Okay. That a little bit bigger. All right, what's the distance between the centers? This is a fun problem. I like this problem a lot. You have to be a little bit clever here. It's not something necessarily that I could really teach you. I mean, I'm going to show you how I do it, but this is a puzzle that's fun to solve. As you can see that these are tangents here. Tangents to...
Could you draw a triangle from the smaller radius, the 2.4 radius, to the point of tangency on the larger circle, to the one that has the measure between that, and that's a right triangle with 2 legs. So then you can find the length of that. Then you could do it for the other triangle in that quadrilateral, and then you could find that length using Pythagorean's theorem, because you know that they're... Oh, no, never mind, you can't. No, you can't.
Give me what you do it, and you tell me what you get.
No, you can't do that, never mind, because that's not the, from the center to the center to one of the radiuses is not right
Is
angle.
everybody onto it? If you can post your answer in the chat if you want. The chat is public, huh? I should be making it just with the host. I just changed it back to host. Okay, so some answers are starting to come in. David, what did you do to get your answer? I don't know. Oh, no, that's not right. It's not 26.5.
I figured that if we extended them and made diameters, they would have 4 right angles.
Okay. It still doesn't give you the distance between the centers, though.
If you find the distance from the center of the smaller circle to the tangent point of the larger circle, that's the same as the Pythagorean theorem applied to the distance between the centers and to the distance from the center of the larger circle to the tangent point, which is supposed to give you the same answer, and you could use the Pythagorean theorem to find it.
No, you couldn't, because
but
that's not a right angle.
You're assuming that this forms a right angle with the 9.3. Which it doesn't.
No, we're not. We're assuming that the right angle is the one that's formed between the 2.4 and the 26.5.
You mean this right angle and connecting this to here, right?
Yes.
Yeah, so this triangle, you could find that distance. But then when you connect the centers, which is the distance you need, this is not a right triangle here, nor would this distance and here be a right. You wouldn't even have a right triangle at all when you make that triangle.
Wait, if you make a line tangent to the big circle from the center of the little circle, you can draw a straight line from the 2 center points, and you can try using the...
What do you mean? Wait. How am I going to draw a line tangent from this point to the bigger circle? You're going to cut across this circle, and it's not necessarily going to be at that point. It won't be at that point since there's only one tangent line at that point. There can't be a second tangent line at that same point. All right, should I give away the hint? Nobody got it? Here's the hint. You're gonna say, oh man, I should have gotten that. Ready? Construct a segment parallel to the 26.5 through a point. And if this one was perpendicular to this transversal, then this one was. And same thing here. You have a rectangle now. This rectangle has the same on both of these sides, is 2.4. And this side is 26.5. Okay? Oop. Okay, butchered that one. Okay, so now you can draw this. The one we need to find is that. Okay, we need to find that. What are you going to do?
Well, you would subtract 2.4 from 9.
This one up here in pink is 26.5.
But if you use the Pythagorean theorem for 26.5 and 9.3 minus 2.4, then that would give the
9.3 minus 2.4 is what? 6.9? 6.9. Okay, so 9.3 minus this 2.4 gives you this piece here, 6.9. That's this piece. This, since this is a right angle here, then on this side you have a right angle. Now you have a right triangle. 6.9 is a leg. 26.5 is a leg. The distance between the centers here is the hypotenuse. This is going to be the answer we are searching for. Go ahead and calculate it. Let's see what we get. Square root 27.4.
7.4 inches.
That was interesting.
Yeah, I mean, that little drawing a rectangle from here to here was a really cool solution for that. I didn't come up with that on my own. That was how the original, that older textbook solved it. Okay, and so that was a nice, just, oh, you know, and it's easier to understand. It's not easy to understand, but it's, once you do that part, then it makes it easy to do the problem. Are there any questions about that? All right, so, I mean, in a bicycle, are the two centers connected between gears? Is there a chain that goes around here? Is one of them attached to pedals, right? You're pedaling. The chain is, you could think of it as tangent to your gear that you're pedaling. As you're pedaling, you're moving the gear in a circle, which is taking the chain around, right? So then this middle point to that center point of the gear that's driving the back wheel of your bike, right? So this is where you're pedaling. Your front tire is over here. So this is where you're generating power, right? With your legs. Your legs are the source of power. Your force of your leg power is turning this circle, right? But the gears that have on your bike are back here, right? So this is driving this bigger wheel around, right? And there are many, many gear type problems in engineering, all right? We saw that video on the differential of a car and things like that. So, but what is this? This is that line of connection between the center points of the gear and your pedal. Okay, that's that distance. Now, if we've studied that further, there's probably ratios that you want to follow to get the maximum performance from your bicycle or from your car, or things like that. So you could see where once you start to study engineering, this is going to go a long way. This is going to go a real long way. Okay. And we're almost out of time. Let's see what we have next. Oh, the converse. We'll start with the converse. Let's go to office hours. Great job, everybody. Dismissed. Now we are in office.
Thank you,
Thank you, Mr. Rosenthal.
You got it.
Thank you.
Thank you.
You got it.
Mr. Rosenthal, I have a question.
Sure.
So Friday is like Cesar Chavez Day, and then next week is technically spring break. So are you still gonna be teaching?
No.
during that time?
Nope.
No?
We are off.
Okay.
We're off. Thursday is our last day of Zoom until we come back from spring break.
Okay. Thanks. Bye, Mr. Rosenthal.
All right, so I'm on live office hours right now. So if you guys have any questions about anything, I'm here for you. Otherwise, once everybody's checked out, I will close this session down.
Okay, thank you, Mr. Rosenthal.
Bye.
Bye.
Mr. Rosenthal.
Yes, sir.
In case you wanted to prepare it for tomorrow,
Let's just do it now and people could see it when they watch the video.
Okay. I know.
You want it live though, I think.
It's a sphere. Yeah, we can do it tomorrow. It's a sphere with a arc 50 degrees and 10 meters long. And you need to find the volume and surface area of the sphere.
Okay, so we need the radius, right?
Yeah.
Okay. So 50 out of 360. So 5 out of 36 of the circle is equal to 10 out of circumference. Okay. So the properties of proportions, if this is times 2, then this is times 2. So it's 72. 72 is the circumference. So then divided by d, or divided by pi, 72 over pi is the diameter. And then I want the radius. So I want divided by 2. So 36 over pi is the radius. And now I can plug that into my formulas. 4 pi r squared. And my volume is going to be 4/3 pi r cubed. And then I would use this value and plug it in. Yeah. I like it. Yeah, we could throw that up there on a warm-up.
Okay. All right. Bye, Mr. Rosenthal.
Bye. Have a good day today.
Okay.
Thank you, Mr. Rosenthal. Have a good day. See you tomorrow.
You got it. Anybody? You guys are hanging out? Who's adult Sanders? That's the same as young Sanders. Who is that? Got to remove you. Mitchell, Nate, Sophia, you're hanging around? Or maybe you left your computer on? Mitchell, Nate, questions? All right, no questions. I'm going to end the session. Ending in 3, 2, 1.